Hello, this is Miraj Patel, and today I will be introducing kinematics. This is my first video of my line of physics videos, and today we will be talking about some of the basic formulas and how they are made, and some simple graphical analysis. So, before we get started, let's first talk about what kinematics is. And kinematics is the study of motion, and it comes from the Greek language, and kina means motion. And in kinematics, we use MKS units. You possibly have heard of this. MKS stands for meter, kilogram, second. So those are the base units of all our calculations. So we're going to be using meters, kilograms, and seconds. And so kinematics has several variables. There's velocity, acceleration, there's displacement, there's time. So the first one, velocity, is a vector quantity, and it has a speed or magnitude and a direction. So velocity is pretty much speed but with a direction. So either positive or negative. So positive would be in like to the right, and then usually a negative is like to the left. And then also there's acceleration, and you've probably heard like people in when they're driving they say accelerate, accelerate, and most people just think that accelerate means to go faster, but acceleration is actually a change in velocity. So any change in velocity is acceleration. So it could be speed up or slow down. So even when you're braking, technically you're accelerating. And it's also a vector like velocity, and it has a direction component and a magnitude. So acceleration, velocity are both vectors, meaning they have a magnitude and direction. And the magnitude, velocity is speed. The magnitude of acceleration is the number, and then the direction is positive or negative, meaning to the right or up. Up and to the right is positive, and down and to the left is negative. So just think of a Cartesian coordinate system. So the uh, positive units, and then the negative quadrants. And lastly, if velocity and acceleration are in the same direction, that means that a car is traveling east and it accelerates also in the east, it will speed up. But if velocity and acceleration are opposite directions, that means acceleration is pointing the opposite direction. So like if the car is going east, it accelerates to the west, then it slows down. So here's an illustration of what I just said. So velocity and acceleration, they're both vectors, hence they have arrows and lengths. And so here we have a car, and it's traveling in the positive direction, hence this quadrant or quadrant 1. And so since they're both going the same direction, this car will speed up because acceleration and velocity point in the same direction. But in this scenario, the car is still traveling to the right, but since acceleration is to the left, it will actually slow down. This car here is traveling to the left, so negative direction, but acceleration is positive, so this car is going to slow down. And then this car is traveling in the negative direction, and it's also accelerating in the negative direction, so it's going to go faster in the negative direction. So velocity and acceleration are both vectors, and it's important to know velocity is speed and direction. Speed is magnitude, and then the sign is the direction. Acceleration is also a vector. If they're in the same direction, they speed up. If they're opposite, they slow down. Okay, and so here are the other variables used in kinematics: distance, displacement, and time. So distance and displacement seem pretty similar, but they're actually a little different. Distance is meant by the total overall length the object travels. So let's just say there's um, someone traveling around a track. So a track is a circle. So the total distance would be the total length of the track. So if we had a 400-meter track and they made one lap, the distance would be 400 meters. But displacement is the change in position between the initial and final point. So if they made one lap around the track, the displacement is 0 technically because they ended up right in the same spot they started. So distance and displacement are slightly different. Seem pretty similar, but they're pretty different. So in kinematics, we're going to be using displacement. So the change in position is always what in kinematics is important. And lastly, time in our formulas is pretty straightforward. Time is, how long did it take for something to happen. And pretty much in our formulas, it's really elapsed time, which is amount of time pretty much over duration of a period. So like if the car took 3 seconds, or the car started at 5 o'clock and moved 300 meters in at 5:01 or something like that. Pretty much we don't really care about the 5 o'clock part. We just care about how much time it took between the 2 points. So it'd be like 1 second in that case. So these are pretty much the variables we need. And in kinematics formulas, there's 5 variables. There's velocity, acceleration, initial velocity, final velocity, acceleration, time, and displacement. So these are the 5 variables we use in the formulas. So now here's an example of what I mean by displacement and distance. So let's look at C and D because they really illustrate it. So C travels all the way to 10, back, and then forward. So the total distance that traveled is 2 to 10, which is 8 meters, then back 2, and then forward 2. So it traveled 12 meters total, but the displacement, or the change in position, is only 8 meters because it's from 2 to 10. So that's the difference. And same thing with D. D was at 7 and moved to 3. So 9 to 3. So 9 to 3 is 6. And then it went back 2 meters. So the distance it traveled was 8, but the displacement is only a 4. So that's the difference. So now we're going to look at one graph, and we're going to derive a few of our formulas. So the first and most popular graph in kinematics is velocity versus time. So here we have a graph, and time is on the x-axis, velocity is on the y-axis. And so from this graph we can analyze a few things. We can analyze the slope and area. So the slope of a velocity versus time graph is acceleration. Because if we divide the units for velocity, which by the way I forgot to mention is meters per second, because how fast you traveled in a given time, or how far you traveled in a given amount of time, so meters per second. And if we divide this by time, so if you think about it, meters per second times the reciprocal of time, which is 1 over s, gives you meters per second squared. And by the way, meters per second squared is the unit for acceleration. So if we use the slope from velocity versus time graph, we always get acceleration. The area, on the other hand, is displacement, because if we multiply the units of velocity, meters per second, and time, we get distance in meters, because the s's here, the seconds, cancel out. So if we just get the area, it's actually just distance or meters. Okay, so using this information we have, let's find out displacement at different times. So at 1 second here, the object traveled how far? So 1 second, we see it traveled 4 meters per second. So how do we get displacement? And I just told you that it was just the area. So everyone knows an area of a triangle is 1/2 base times height. So 1/2 times 1, because it was 1 second, times 4, because the height, it was at 4 meters per second. So if we do that, 1/2 times 4 times 1, it gives us 2 meters. So in the first second, the object traveled 2 meters, okay? So in the second, after 2 seconds, how far did it travel? So it's the same thing, it's still a triangle, so 1/2 base times height. So the 1/2 base is 2, height is 8. So 1/2 times 2 is 1, and then we're left over with 8. So after 2 seconds, it traveled 8 meters. So if we do that, we get 1/2, and then if we do that for 3 seconds, 4 seconds, 5 seconds, we get 1/2 times 3 times 12. So 6 times 3 is 18, 1/2 of 12. Okay, if we do 1/2 times 16 times 4, it's 32, and if we do 1/2 times 20 times 5, it's 50. So if we do that, we get these values, and so notice how they're just what I said. So we calculate it using area, but one of our kinematics equations is pretty much just like what we did. So it's pretty much displacement equals final velocity minus initial velocity divided by 2 times time, which looks like the area of a triangle, which is 1/2 base times height. See, the 1/2 is this 2 here, and time could be like, time is the base in this case, and then the height is the change in velocity. And so pretty much, since we always started out with initial velocity of 0, pretty much we only had one value for this. So that's how we get the average velocity equation. So pretty much you take the final velocity minus initial, divide by 2, so that's pretty much an average, and multiply by the time. And so this is how we get displacement, just like we calculated. Okay, so there's another type of graph, which is a displacement versus time graph. And displacement versus time graph plots time on the x-axis and displacement, or how far it's away from its initial point, on the y-axis. From this, we can analyze the slope. So the slope of a displacement versus time graph is just velocity. And you can get this because meters, which is the unit for displacement, divided by time is meters per second. So meters per second is a unit of velocity. So this is how you know the slope is velocity. And second, in this case, the area doesn't really have a meaning because there's no unit with meters and seconds multiplied. There's no meter second in kinematics right here. Okay, so this last formula here we're going to derive is cool because it can be derived by looking at displacement versus time graph. And so here we have our chart here. So we have the times, we have the velocities, displacement. And notice how displacement is quadratic with respect to time. So that means displacement, notice how it gets larger and larger and larger, like almost like it's sort of exponentially. But if you look at this pattern here, if I square the time here and multiply it by half the acceleration, this is all that's saying, we get the exact measurement of displacement. So the acceleration in this case was 4 meters per second because the slope of this line is 4. So because notice how after rise over run, so 4, I traveled 4 up, and then I moved 1 second in time forward, so it's 4 over 1. That's the slope of this line. So if I go back, so pretty much half the acceleration is 2, and if I multiply by the time squared, I get exactly the displacement, just like here. So this formula for kinematics is known as Galileo's equation, and this is the whole formula. So displacement is initial velocity times time plus 1/2 at squared, so acceleration and time squared. And in this case, we ignored the first part because our initial velocity was 0. We called it in all of them because at time equals 0, the velocity was 0. So since we had a 0 here, we ignored the first part. So that's why this part is the important part we used. And notice if I graph it with time squared as the x-axis, we get a straight line. It's because displacement was quadratic with time, so if I make time squared, it'll be a perfect line. And in my class, in my AP, in my class, it's an algebra-based AP physics class, so we don't deal with calculus or any curves, because if I didn't do this, it would have been a curve if I just left it with seconds at the bottom like it's supposed to be. But with this time squared, it was actually a perfect line. So the last equation we learned about was the energy formula. And the energy formula is derived from Galileo's formula and another kinematics formula, whichever one you want to use. And we basically just cancel out time and solve for v sub f squared. And so pretty much this formula says final velocity squared is equal to initial velocity squared plus 2 times acceleration in time. And so this is our last formula, and the useful part about this is you don't need to know anything about the time. You just need to know about the initial, final, acceleration, and then the path it took to get there. And so pretty much in kinematics, you need to know these 4 equations, and it's good to be familiar with these. And so we learned the definition of acceleration, which is acceleration is final velocity minus initial velocity over time. So pretty much it's change in velocity over time. Average velocity is final, actually that should be a plus sign, final plus initial over 2 times t. Sorry about that typo. Galileo's equation is initial velocity times time plus 1/2 acceleration times time squared is displacement. And this is the cool formula based off of that time squared is proportional to displacement. And then energy equation, which I just told you, is based off of a combination of these three top formulas. But you don't really need energy to solve kinematics formulas, but instead of using two equations, you can just use this one. So thank you for listening to my physics videos. This is Miraj Patel, and today was an introduction to kinematics and the four formulas. And so we talked about pretty much how to derive them. If you don't understand them, please ask me any questions at my email right there. And the next video we'll be talking about how to solve problems with these kinematic formulas. And if you enjoyed this video, please share it with your friends and like this video down below. And again, email me any questions you have about kinematics or any physics related questions. And if you want, check out my chemistry tutorials if you're taking chemistry, and visit my website, buccaneerchemistry.weebly.com. Thank you and have a great day. And thank you for listening, and have a great day. And we'll see you next time.